All right, still in chapter 2.6, we're going to talk about rational inequalities and then rational equations. And I'm starting with inequalities first because we just got finished with rational expressions and simplifying those. And rational inequalities continue to work with those expressions. So we're going to do what we did for polynomial inequalities and just look at graphically what's happening. And I actually have two inequalities to compare. So here's our first one. This is also good practice at correctly typing in um, a rational expression to your calculator. So remember that you need parentheses to tell the calculator that this entire numerator is together. It's one piece. Otherwise, the calculator does not know, and it just, and it does order of operations. I need to insert a plus sign, so I'm going to do second delete, and then plus, and then arrow out of that. That's a little trick to insert something if you had a lot typed and you don't want to retype the whole thing. All right, so here's the numerator, and then divided by, you need parentheses around the denominator too. And we're not going to type in the greater than 0. There is a way in here somewhere to change this to inequalities, but let's just zoom 6. Let's just zoom standard and see what this graph looks like. We can adjust if we need to from there. So this is kind of a weird graph. Here's this graph. We haven't talked about the graphs of rational expressions yet, but I know that you did rational functions last year. So remember, if x minus 1 is in the denominator, you would have this vertical asymptote at x equals 1. This problem says, when is this rational expression greater than or equal to 0? Remember, if you're looking at a graph, that equates to above the x-axis, or equal to is, where does it hit the x-axis? Or in other words, you're looking for, where is this expression positive? So if we look at this, it looks like it's between -3, and then there's a bounce at 0, and then kind of shoots off up into space here because of this vertical asymptote. There may be 2 to infinity. So I don't want to take the time to find all these zeros. So because I think they're integers, I'm going to go to the table. So second graph. Yeah, so my table says that, yes, -3 is a 0, 0 is a 0, and 1 is an error, so that's the vertical asymptote, 2 is a 0. So if I'm looking at this, let me split screen so I don't have to keep going back and forth. If I'm going back to the graph, where is this graph above the x-axis? So let's use interval notation. It's greater than or equal to, so square bracket. The graph is above the x-axis from -3. We don't want to say -3 to 0, 0 to 1. We want to say -3 all the way to 1, but not including, because the graph is touching the x-axis at 0, and this says greater than or equal to. If it just said greater than, I would say to 0, 0 to 1. And I'm not including 1 because remember, 1 was an error, not defined. If you plug in 1, you'll divide by 0. There's another piece to this. It looks like x equals 2. Yep. At x equals 2, and then anything to the right of that, this graph will shoot up beyond, without bound. So from 2 to infinity, this graph will stay positive. Okay, so what about, take a look at the other inequality that I gave you. This is just the numerator of that last inequality. So what I'm trying to look at here is, am I going to just get the same answer? Because what we often want to do when we're solving for these is like, oh, I'll just multiply the x minus 1 over to this side, and since it's times 0, I get this. So let's investigate that. Let's see if we get the same answer. Really, you can just go and, unless you want to recall this again, you can just delete these last few keystrokes instead of retyping the whole thing. I think the parentheses are okay. When is this graph greater than or equal to 0? When is it above the x-axis or touching the x-axis? So here it looks like to the left of -3. And then we do have that 0, 0. We do have 2, 0 to infinity. So for this one, the solution set is -infinity to -3. And then don't forget about that individual point 0, because greater than or equal to 0. And then 2 to infinity. So what I'm trying to point out here before we dive into the rules is that these two graphs did have one section in common. So think about the numbers 2 to infinity. If you plug in 2 into the numerator, you're going to get something positive, right? 16 plus 8 minus 24. Oh, I guess that's 0. Duh. If you plug in like 3, you're going to get 3 to the 4th. So what is that? 81 plus 27 minus 54 is still going to be something positive. And then if you plug in 3 to the denominator, you're also going to get something positive. So in this section, you get this positive divided by a positive, which is always positive. And that's happening too here. You get a positive in general. But then what's happening in this -3 to 1 section? So let's just look at 0 because that's easy to plug in, right? Or no, not 0. I keep picking the zeros. I want to pick something with a sign. Let's pick -1. If we plug in -1 into this function, we would get 1 -1 -6. So that's negative overall. And if you plug in -1 into the denominator, -1 minus 1 is negative. So even though the numerator is negative and the denominator is negative, they divide out to become a positive. And we want all of the sections where this entire expression is positive. So that's why this little section here also gives us positives. If we take away the x minus 1, the reason -3 to 1 was not in this solution set, 0 was, but none of the other values, is because you're going to get this negative value, right? This whole thing is negative on -3 to 1. But there's no negative to divide it by to turn it around and be positive. And same thing here, there's this extra positive section where like from -3 to -infinity, you get something positive out of this, but you get something negative if you divide it by x minus 1. So overall, that's a negative. So what I'm trying to get at, was the solution set the same for the two inequalities? No. I'm going to write this. The divided by x minus 1 causes some sign changes. That's kind of a poor way to explain that, but if you're comparing the numerators, when you divide by x minus 1, sometimes that makes you divide by a negative, and sometimes that turns things around, right? So because of that, what I'm trying to point out here is that you are not allowed, if you're solving a rational inequality, you're absolutely not allowed to multiply an x or a variable or whatever, a denominator, over to the other side. You cannot clear the fractions. So the first step is get the inequality compared to 0 if it's not already. So subtract a 2 or whatever. And then if you need to, simplify to a single rational expression. So we're going to see in some of these problems, we've got a bit of work to do to get this to a single rational expression. I want to make a note here. So never multiply denominator to other side. The reason that this is confusing and becomes such an easy mistake to make is because when we do solve equations on the back of this piece of notes, we will be able to do that. So anyway, I don't want to get too ahead of myself, but anyway, we need to keep the fraction. So once you get this fraction, you have this little fraction on one side, find the x-intercepts. That's going to be where the numerator equals 0, could be more than one place. And find the vertical asymptotes. Again, I know that we haven't talked about graphs. We're going to talk about rational graphs tomorrow. But if we're looking for vertical asymptotes, we're looking for where the denominator, oh, sorry, I don't want to write this here. Where the denominator equals 0. And these numbers that we get, the x-intercepts and the vertical asymptotes, they're called critical numbers. You're going to use that terminology in calculus next year too. So we use rational inequalities all the time in calculus. So you take these critical numbers, you plot them on a number line, and then because these graphs are complicated, I do not want to sketch this graph. Well, that one's not terrible. That one's not great, but I don't want to sketch the other graph that was like divided by x minus 1. I'm not going to go through and make it, but anyway, I don't want to do that because that's not quick and easy. It's not just end behavior and multiplicity. So instead of doing the graphs, we have to just do this numerically and test numbers in each interval. Every interval between all the critical numbers that you plotted. So the graph will be always positive in that interval or always negative. It will not switch back and forth between zeros and vertical asymptotes. So we just want to make note of where it's positive and negative. And then based on the inequality, we will give our answer for our solution set. So let's just go through a few examples. They're all kind of the same. So once you get the steps down, it's pretty straightforward. So get the inequality compared to 0. This one already is. Simplify to a single rational expression. This one already is. There's no like plus something else involved. Find the x-intercepts by setting the numerator equal to 0. And it might be smart to name this an x-intercept. You'll see why in a minute. Excuse me. And find the vertical asymptotes. We'll call that VA. If x plus 3 equals 0, x equals negative 3. The reason it's important to distinguish between the two is because you're going to put these critical numbers on a number line. So let's do that just off to the right side here. Make sure you put them in order. So negative 3 has to be to the left of positive 5. Here's where it matters as far as marking these down. We're looking for when is this fraction less than or equal to 0. In other words, when is this fraction below or negative the x-axis, and when is it hitting the x-axis? So when we plug in 5, that x-intercept is when the function is equal to 0. But remember, we can't plug in negative 3. That's one of the domain, or that is the only domain restriction on this rational expression. So we plot that with an open circle because negative 3 cannot be part of the solution set. It can't actually be plugged in. You'll be dividing by 0. And then again, I do not quickly off the top of my head know what this graph looks like. So I will just plug in, I've got 3 test intervals here. I want to plug in and see what happens to the left of negative 3 with this graph. You can pick any number to the left of negative 3. I'm going to choose negative 4. But any other number to the left of negative 3 will behave the same way. So if I plug in negative 4, I get negative 9 on top, negative 1 on the bottom. That's dividing out overall to positive. Picking between negative 3 and 5, 0 is my favorite number to pick. It's easy to plug in. You get negative 5 over positive 3. It's the fact that that's negative that's important, not the numerical value. And then if you plug in 6, you're going to get 1 over 9. That's positive. We want the negative section, so our solution set is the only negative section, which was between negative 3 and positive 5. The good thing about this is you can check your answers. Pick a number between negative 3 and positive 5 and just double check that it's less than or equal to 0. Pick a number in the other two. It's kind of what you're already doing, but double check, pick a different number in the other two and see if it's coming out correctly. All right, number 4, get the inequality compared to 0. Right now it's not, it's being compared to 3. So the first thing we need to do is subtract 3 to the other side. And right now I just have to write that like this because I don't have a common denominator. But remember, the other part of step 1 is get the inequality compared to 0, done. Simplify to a single rational expression. We need to know how this entire side compares to 0, and it's so much easier to do if you have it down to one fraction. So go through the work of setting up the common denominator. This negative 3 is going to get multiplied by x minus 5 so that this whole thing can be over x minus 5. Remember, we are not allowed to multiply any of these denominators to the other side. So it would be wrong to say 2x minus 7 is greater than 3x minus 15. You might get part of the answer, but you'll be missing the other part. So this is 2x minus 7 minus 3x plus 15 over x minus 5 greater than 0. Simplify this, negative x plus 8 over x minus 5 greater than 0. So all of this was step 1. Get this compared to 0, subtract 3, get it down to one fraction. From this point, find your critical numbers. So the x-intercept comes from the numerator. When is negative x plus 8 equal to 0? I would just add x to the other side when x equals 8. The vertical asymptote is when x minus 5 equals 0, x equals 5. Get these on a number line. 5 is to the left of 8. 8 was the x-intercept, but we're just looking for greater than only, so above, but we're not including 0, and we're looking for positives, by the way. Above the x-axis are positive. We're not looking at 0, so actually I'm going to put an open circle at 8, and then I have to put an open circle at 5 no matter what, because 5 is the one value that we cannot plug in so that we're not dividing by 0. When you're testing numbers in these three intervals, you're testing into the single fraction. Otherwise, if you're going to test, it's harder to test into the original because then you have to do the math and make sure that the number you got is greater than 3 or not greater than 3, and that can get complicated. So much easier just to come out positive or negative. So to the left of 5 is 0 this time. If I plug in 0, I get 8 over negative 5, negative. In between 5 and 8, I'm going to pick 6. Negative 6 plus 8 over 6 minus 5. That's 2 over 1, positive. Pick 9. Negative 9 plus 8 is negative 1. 9 minus 5 is 4. Now, it is true that often these signs are going to alternate, but that's not always true. We had an area where, for this one that we graphed on our calculator, where we had like a touch and turn or a bounce at 0. So we had to, like, this would have been plus, plus, minus at some point. For this one, we want the positive section, so this one happens to be in the middle again. Not all of these solutions are going to be in the middle, so I'm basically just trying to get the point across that there are no shortcuts. You have to go through these steps. But the good news is, like I said, the steps are essentially always the same. The only thing that's different is getting the thing down to one fraction. Again, for number 5, I cannot just like cross multiply and get rid of fractions. Instead, I have to get this compared to 0. I always move expressions to the left side. It's just usually easier for my brain to work like that, but it doesn't matter. We need to get this to one fraction, so 6 is going to get multiplied by x minus 2. Negative 1 is going to get multiplied by x minus 5, so that they both are over this common denominator, x minus 5, x minus 2. And we're still saying this is less than or equal to 0. I should be putting equal sign. Oh, no, I shouldn't. What am I doing? No equal signs. These are inequalities. So I should be distributing 6x minus 12 minus x plus 5. Remember, there's no need to distribute the denominator together. So we've got 5x minus 7 over x minus 5, x minus 2. It is possible, like in this one, that you're going to get some fractions for your critical numbers. So the x-intercept is x equals 7/5. And then there are two vertical asymptotes, 5 and 2. So, and again, you might want to compare 7/5. This is the one time I like really encourage mixed numbers because you need to correctly place this. So that's 1 and 2/5, right? So when you're putting these on a number line, I'm going to bring my number line up here. What's furthest to the left? 7/5, or 1 and 2/5. And then 2. Actually, you know what? I'm going to write this as 1 and 2/5. Anyway, and then 2, and then 5. 5 and 2 came from the denominator. 1 and 2/5 is the 0, and this is less than or equal to 0, so that gets filled in. Okay, so this is easy. To the left of 1 and 2/5 is 0. Remember, you're testing into this thing. And it's just the positive and negative signs that matter. So doing the math isn't too bad on this one, but when I plug in 0, I get negative 7. And then remember, you're multiplying these together. 0 minus 5, so negative 5 times negative 2. That's negative 7 over positive 10. Whether or not you simplify that to negative 7/10 does not matter to me. It's just that you need to be able to pull out the fact that that's negative. Now we need something between 1 and 2/5 and 2. Now remember, 1.5 is slightly bigger than 1 and 2/5. 1 and 2/5 is like 1 and 4/10, so 1.4 compared to 1.5. Okay, so I'm going to plug in 1.5 or maybe 3/2. Actually, no, I do want to leave it as 1.5 because I want to point something out. So this is going to be 5 times 1.5, or okay, maybe here, 3/2, minus 7. And then 1.5 minus 5, 1.5 minus 2. I'm assuming that we're doing this all without a calculator, by the way, so we need to make sure that we can do this math. So just think about what's happening here. So this is 15/2. 15/2, what is that as a mixed number? 15/2 is 7.5, right? So 14 divided by 2 is 7. 16 divided by 2 is 8. So 15 divided by 2 is 7.5 minus 7. The whole point is that's positive. What about down here? 1.5 minus 5. Yeah, I could do that subtraction, but I'm just saying, well, it's negative something. And 1.5 minus 2 is negative. A negative times a negative is a positive. So you're going to get a positive divided by a positive. So again, you can, not that the math is like really all that difficult here. I could have figured out this value, but you do not need to waste time actually calculating the numerical value. You just need the sign. That's the only thing that's important. Something between 2 and 5. I'm going to pick 3. 3 times 5 is 15 minus 7. 3 minus 5 is negative 2. 3 minus 2 is 1. Positive 8 divided by negative 2. So I'm not going to bother simplifying that. It's just negative. Something to the right of 5 is 6. 30 minus 7, definitely positive, over 1 times 4. Positive, 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 all around. And we want this is less than, so we want the negatives. Or if we were to graph this, when is it below the x-axis? So I'm shading in those intervals, and I'm going to answer over here. Negative infinity to, maybe I'll go back to the 7/5 on this one. Square bracket, because it's less than or equal to, and then 2 to 5. Now, rational inequalities are the long, complicated ones. Rational equations we like because they're much faster. So the first thing you need to do is just make a note, whether you write this down or not, up to you. Make a note of the domain restrictions, meaning the denominator, remember these are rational, the denominator can't equal 0, and then you solve. If it turns out that x can't equal 2, for example, and then you go through and solve this thing and you get x equals 2, that can't be in your final solution. So you might get no solution. If it can't be in the final solution, it's called an extraneous solution. It is a solution, except that it can't be because it's not in the domain. So even though we got it, because we're about to be multiplying denominators out of the way, we have these solutions that could be extraneous. All right. So here you are getting rid of the fractions. Clear all fractions. Equations have different rules than inequalities, because inequalities you're comparing one side to the other, and that means that signs, positives and negatives, are at play and they matter. And with equations, we're just finding points of intersection. So we're just saying, where do these two things cross? We're allowed to clear out the fractions. And then you just solve. So it could be that you get a nice linear equation. You might have to do quadratic formula. Maybe you've got a factor or something. So just pay attention to the rest of the solving piece. With all of that said, let's take note. I almost got started without making my note here. My note is that x can't equal what? X can't equal 0 or negative 1 because of those two denominators. So we just need to make a note of that. If we get either of those answers in the end, we're going to say no solution. Or we're going to throw out that answer at least. The common denominator for these two fractions is x times x plus 1. So you're allowed to multiply both sides of an equation by the same thing so that you're keeping the equation balanced. And that would make this 4 times x plus 1 minus 3 times x equals 1 times x plus 1. Okay, So we've done steps 1 and 2. Now we just have to solve the equation. So I'm going to distribute 4x plus 4 minus 3x equals x squared plus x. The left side here is really just x plus 4. I like my quadratic term to be positive, so I'm going to move everything to the right. X squared, oh, actually, I'm not going to move everything to the right. If I subtract x to the other side, I get x squared plus 0x minus 4. I guess I'll do that. So this is a quick difference of squares. X equals plus or minus 2. But before I box this in, I have to say, wait a minute, double check. Are either of those values restricted from the domain? The answer is no. I got x equals plus or minus 2. The only answers that were not going to work were 0 and negative 1, so this checks out. All right, next one. Here's a little twist to this one. First of all, factor this trinomial. This is x minus 3x minus 2. And then take a look, I'm not going to write that second part down yet. Take a look at your other two denominators. So I have x minus 3, x minus 2, x minus 2. Is 3 minus x really different than x minus 3? We've seen this before. I kind of call this like a backwards factor. We're used to seeing x come first. So instead of saying minus 2 over 3 minus x, we're allowed to factor a negative out of 3 minus x so that it looks right to us. It looks like x minus 3. And then what that really does is it says, well, you had a negative there already. You factored out a negative. So this is really now plus 2 over x minus 3. So anytime you have what I call a backwards factor, it's a good idea to rearrange it. You certainly wouldn't want to make the common denominator x minus 3, x minus 2, 3 minus x, because then you're going to have a problem that's much more complicated. That was not the least common denominator. All right, so once I've straightened this out, now I can show that I'm just going to multiply by the LCD, which is just x minus 2, x minus 3 on both sides. And on this first term, the whole denominator cancels. You get 6. Then you're going to get plus 2 times just the x minus 2. And that equals 2 times just the x minus 3. And this is going to be a nice linear equation to solve. I'm getting 2x plus 2 equals 2x minus 6. Are those two things ever going to be equal? Think about those lines. Is this line ever going to cross with this line? They have the same slope. They have different y-intercepts. There is no solution to this. Maybe you're not thinking graphically, though. If you're just going through the motions, you might say, well, the x's cancel. I get like 0 equals negative 8 if I get the numbers to the right side. Well, that's not true either. So if you're left with an equation that doesn't actually come out to 0 equals 0, then the answer is no solution. If we were to graph the original equation, when is the left side equal to the right side, we would just see that there are no points of intersection. All right, number 8. I'm allowed to cross multiply here, if you want to think of it that way. You could factor out an x minus 1, or factor out a 2 and show that that's x minus 1, if you want to. But honestly, if I see a fraction equal to a fraction, I would just cross multiply. So I would just say 5x squared minus 5 equals, I'm just going to keep this as 2x minus 2, equals 30x minus 30. It's quadratic, right? So, oh, I could divide by 5. How about we do that? So we'll simplify in that respect. We can divide both sides of an equation by 5. So that makes it x squared minus 1 equals 6x minus 6. It's quadratic, so we need to get this equal to 0. Add 6 to negative 1, you get plus 5. That's going to be x minus 5, x minus 1. X equals 5 and 1. Oh, you know what I didn't do in this problem? Or the last one, really. I didn't make note of my extraneous solutions. Now, in 7, it didn't matter, but in 7, just to note, if we were solving, x can't equal 2 or 3. because that's what makes the um, denominators equal to 0, but it didn't matter for that one. What about for this one? X can't equal positive 1 or plus or minus 1, so in general, plus or minus 1. And then my solution set says x equals 5 and 1. So actually, this 1 right here is an extraneous solution. That means that only x equals 5 is an intersection point. Because if I were to plug in 1, the reason that's coming out as a solution is because that's the value that makes both pieces undefined. So they have that in common, but it's not a solution. Okay, that's it for today. We're going to practice some of this, and then we're going to get into graphing in the next couple of days. If you have any questions, please come to office hours or ask me during class.